In this lecture, we are going to talk about the thread strength of a power screw. Uh, so as we begin our discussion here, what we have to keep in mind is you have a power screw that has all kinds of loads here, has a load here and here. And each one of these threads is carrying all the load. And we want to know what happens to one of these threads, right? Well, we want to know how to design these threads. And we know that these threads are going to be subject to loads, both in static, so we have to make sure it's safe in static. Also, it's going to be subject to loss and fatigue because most likely, if we say power screw, it's going to go up and it's going to go down. So one case it will be in compression, one case you're going to be in tension. So we want to analyze this problem like this. And basically, what you have in this problem is you have the axial stresses, the axial nominal stresses, transverse shear stresses, tangential shear stresses, the normal nominal shear stress, and the bearing stress. Um, and these are given by mzz over z. I'm going to skip all the derivation here. That's basically given in your note, in your book. This is 6 times t, and uh, this is the root diameter. This is the number of engaged threads, and this is P. And then this is a 4f pi dr squared, 3 times f, and this expression. And the end of the day, what I really want to point out here that's important is that most of the time the bearing stress is less than your this actual stress, this one right here. And that's why typically we don't check this and we just make sure everything else is it works. However, this is a check that you should do individually, independently. And one of the things I wanted to point out is it looks like you got axial stress, also you got axial stress. However, this axial stress, because the direction is applying is sigma YY, not sigma XX. Okay, I will get to that in a minute in your state of stress, and we learn how to do that. But before I move on, basically what you have in a problem is when you're doing these problems, um, imagine you don't want to design one particular thread of having the full load F, right? So there are certain stresses that only experience 38% of your load, doesn't experience the 100% of your load. So what I'm trying to say is instead of using F, we're going to use for this thread is going to be 0.38 times F, okay? And so you got a load F applied here, and what some of the stress is going to experience only 38%. So it's pointless to put that extra burden on each one of the threads to design them such that you hold the full F when you're really going to experience 38%, because then as you can see here, as you move along the threads, then your distribution becomes smaller and smaller and smaller and smaller. So what we're going to do is we're going to design your first thread, make sure that's safe, and assume all the others are identically the same. Okay. Um, and then another thing we're going to do is, and I want you to imagine that the worst case scenario, let's suppose you have only one engaged thread. Obviously, that's not going to be true, but this is conservative. So I'm going to take n and I'm going to replace n for 1. All the n's are replaced for 1. And the stresses that do change, the experience only 38% are these stresses right here. Okay, all the others that, for instance, for example, this I experienced the full torque. This doesn't experience 38%, neither does this load. Okay, so just have to keep in mind that those stresses need to be modified accordingly. So now as we move into threads, we want to analyze this thread. You can have a case like this, a more general case. You got A, B, and C. 3 locations that we are interested in finding what's going to be safe and what's not going to be safe. So as you can see that for each one of these points, For this point, I'm going to have a state of stress, A. And then for this point, I'm going to have a state of stress, C. And this point is going to have a state of stress, B. Okay? So these are stresses that we need to find. And how do we find the stresses are given in the next chart. And what you can see here is in this particular point A is typically not critical at all, but it's going to actually fail due to wear. And you may want to check that as well because sometimes wear can be a issue. And this is point A and this is point A as well. And just know that it's sigma YY. Okay, this is the direction in a way this is all applied. So then the point B, however, is going to fail likely yield and fatigue. So you need to check those. And if that's the case, your state of stress will be given by this. In this particular case, as you can see, immediately you can have sigma 1 is going to be 0, sigma 2 is going to be 0, and sigma 3 is going to have this value, and because it's negative, right? Just because it's negative, I know I'm going to get a negative value there, and that's going to be your stresses, principal stresses. Here, however, you may have to use your all the techniques learned in this course to find sigma 1, sigma 2, and sigma 3. Okay, and the lastly, this is the most critical point. Okay, and it's most likely failed. Is it will fail if it does to the fatigue, and this is just state of stress that's most complete that you can see, and you can see that if this particular location is completely safe, then the possibilities that this is sigma C, this is safe, then most likely everything else will be safe. Okay, so as we move on now, um, the first thing you want to do in the problem, these are steps on how to resolve this. You want to multiply this by the design factor. So you're going to multiply your load and your torque in the design factor. And for static analysis, you're going to use uh, these factors as start. It's going to be more critical, and that's what you want to do. For fatigue assessment, since it's a running load, it's a cyclic load, then you can use this at running only. Okay, you don't have to do this as start. You're adding extra burden unnecessarily. And don't forget this, that you have to modify your loads properly by the design factor. Okay, so the second step is the static check. Um, okay, I just replaced the slide. So this is your point C, as you can see, that's the point that we want to evaluate. It's always at point C that's going to be the most critical. And basically, once you have a state of stress, what you really want to find is in your static check is sigma 1, sigma 2, and sigma 3. I mean, S1, S2, S3, these are principal stresses. This sigma equivalent is von Mises. So most of the problems when I'm going to solve, I'm probably going to write this as VM in your solutions, but don't get confused by that. So when you're checking for yield, what you want to do in yield, the first check is sigma divided by, this is von Mises, and then this has to be bigger or equal than 1. And then you can also check for shear. It's not necessarily, you don't have to do this check of all. This is just sufficient. However, if you wanted to do it, this is how you will do it. You have to use YS, tau max, and it has to be bigger or equal than 1, as we have always done. Okay, then as we move along, and so when you want to do fatigue, note that in fatigue, you have to always find your alternate loads first, right? Alternate and your mean loads, alternating and your mean loads, you want to find them, alternating and mean torque, and so you can see that you're going to use the corresponding loads here. That's the only thing that's going to change from your previous equations. And then here, don't forget that your coefficient, the coefficient of friction that you will use is at running. Okay, those are the coefficients that you will be using. So now, once we have that, what we want to do is we want to go ahead and we want to find your fatigue stress concentration. Okay, for fatigue stress concentration, we're going to use the fillet radius method, and what we're going to say is this is basically for this type of problems. This is usually the most critical, the maximum that's going to have. So that's the value we will use for our problem. And once we have that, then basically the exercise becomes as we always did. We're going to use tables A15 from your textbook. And, tables A15, just remember they look like this. You're going to use this specifically the one that has fillet. And the way you do this, your big D will be your D, and this D, so just to tell you, D, just a reminder, is your major diameter, and your dr is your root diameter. It's the smallest diameter in your screw. So therefore, this is typically known from your geometry. This is given, and this is also given. The RF is just calculated, and you found this using this equation. So then you can go here and you can find which is the value for your static. Remember, this is going to give you static. Okay, in this case, this is moment you KTB. However, there are cases in which you may not be able to find KF as is will be the case for your homework, for your the example you will do in class. In such a case, you have to go to table A16 to find your KF, but that will be your total KF. So table A16 looks like this, and you would just select what the grade size, the SAE grade that you have. And in our case, we're assuming it's fillet, so you can use these values. And one thing that's important is that this is only for axial loads, okay? And this gives you just the KFA. This is not KTA, so you don't need to modify, you don't have to simplify. So this is only for the axial load, okay? And this will correspond to your sigma YY. That's the value that you're looking for. Okay, so as we move then for the other cases, you will have to go to table 6.2, 20 and 6.21. Find this is your RF value. With your RF value, you'll find the notch sensitivity. And once you have your notch sensitivity, then you can come here and you will be able to find these values. Okay, just note that this value, in some cases, you may be able to just find this value directly from the table 816, as I just told you a few minutes ago. Um, okay, so that's how you will find this. Then once we have our factors, then you're going to just go and find your von Mises for alternating and your mean stresses at point C. That's a critical point. So for your mean stresses, what you will do is you're going to come here and you can see that I multiply. This is your bending. This is your torsion. These are all torsion corresponding to your torsion values. Shear due to torsion. This is what is correspond to your axial, okay, FA, KFA. So this is not a mistake. This is intended to be like that. This is your von Mises. I'm going to typically write this like this. Sometimes I like to write it like this. It's just simpler to avoid confusions as we move along. Once you have that, you want to find the von Mises. Once you got your von Mises, then the first thing you always do is check your static check at the maximum fatigue loads, right? So once you do that, S max will be SA plus SM, and that will be given by this equation right here. Um, Then as you move along, and you want to make sure that this is bigger or equal than 1. If it is, then that means it will not yield, and we are good. Otherwise, you need to stop, you need to redesign. Uh, then you do fatigue assessment using the Goodman theory. That's the theory I recommend, and this is the equation that we use. I like to use this form of the equation because it's bigger or equal than 1. Use yield strength, and then we are safe. Then you want to use infinite life, given a number of life cycles. Find the fatigue factor of safety. SC divided by S equivalent. If this is bigger or equal than 1, then it's infinite life. If it's less than 1, then you have finite life. And all the power screws are typically designed for infinite life. They're never designed for finite life. So this concludes the theory for the thread strength analysis of power screws. And next we're going to do an example.